This meeting is being recorded.
Excellent. So let's start with the afternoon session. Welcome back, everybody. Now we have Adrian, who is going to tell us about the missing theory part, which is, the part that we were missing so far, which is possibly the most complicated aspect at the theoretical level, which is the structure of SU2 interactions, or non-abelian in general, and SU2 in particular for CosmoLattice, and how this works in the continuum and in the implementation in the lattice. So please, Adrian, the stage is yours.
Yeah, that's right. Good morning, everyone. So yeah, as Danny said, this may be a bit of a dense lecture, so don't hesitate to ask questions whenever you have them. I'll start by sort of trying to go relatively quickly through how SU2, from zero, but quickly how SU2 works in the continuum, just so that we are all on the same page and we have common notation. And then I will try to explain how actually you discretize such an non-abelian theory and how you can do numerics with it. So to start with, I'm gonna look at the theory of a SU2 gauge field coupled to a scalar field, a complex scalar field, scalar doublet. And I'm gonna try to remind you how this works at what are the fields, how they transform, and all of that. So the theory I'm gonna consider is this one, trace of G mu nu square, where G mu nu is going to be my SU2 gauge field, and this is the simple generation of the F mu nu of electromagnetism, and then coupled to some scalar doublet, d mu phi dagger, d mu phi. And so when I write that, G mu nu is really my SU2 gauge field, the field strength tensor.
Adrian, question: are you ignoring on purpose metric, space-time metric? You are in
so far I'm doing that in flat space-time, and then I'm going to introduce the FLRW after.
Thanks.
Good point. Yeah, really start from the flat space-time because it's already complicated, and then I'm going to show you that actually FLRW basically like for you want, so it's not too hard. So yeah, G mu nu is really my field strength tensor for the SU2 gauge field, and it goes as an abelian piece, so really like the electromagnetism. But since now it's a matrix that lives in SU2, it also has this commutator part that makes everything more complicated. And both B mu and G mu nu, the two of them lives in the algebra of SU2. I'm gonna write down everything what the group in the algebra are after, but now just take that as a group of matrix. And then my scalar field is just a two-component complex field, and the covariant derivative generalized as follow: d mu phi minus I GB QB B mu acting on phi. And so now phi is really a doublet of complex scalar field. So if you want phi 1, phi 2, and both phi 1 and 2 are like a complex number, complex field. And so the point of this theory is really that this is invariant under local gauge SU2 transformation. Let me write this down. And I'm also going to write down the transformation now.
Sorry, just to clarify, phi 1, phi 2 are different, obviously, in general, despite the fact that you just meant they are complex.
Yep. invariant under a local, namely a gauge SU2 transformation. So this is really the group now. And what I mean by that is that you can take B mu, and now you can transform it something that now doesn't look so much like in the abelian case, but you see that it's not so different, because now if omega was just a phase like in U1, this omega and omega dagger would cancel. And then there is also the derivative part that you use from the U1 group, but now that takes a slightly more complicated form, d mu omega of x, omega of x. And when you do that, the point of doing this transformation is that now the covariant derivative transforms simply, like in U1, and also g mu nu transforms simply. Note that that's also a big difference with U1. In U1, f mu nu doesn't transform, but when you have an abelian field, the field strength tensor does transform like something in the adjoint representation. And just then I'm happy to take any question and to maybe further clarify. The last thing I want to say is maybe just a reminder of what is SU2, both the algebra and the group.
One comment, Adrian, I may be missing a dagger, I think, in the B mu transformation. In the d mu omega times omega, I think there is missing a dagger.
Yeah, that's right. So the Lie algebra is the set of matrices such that the Hermitian matrices with zero trace, 2 by 2, and this characterizes SU2. And correspondingly, the group is the set of 2 by 2 unitary matrices with unit determinant. And this is SU2. And so really, this is simply generalization to a field-valued matrix of electromagnetism. And of course, it's relevant because that's how we think that both the weak and strong forces are described in the standard model, meaning that if you write down the theory, you do its phenomenology, and it describes very well the standard model. Any question now? I think looks okay so far. Hopefully this is just a reminder. So if it's not, then sort of take it for it, and we can start from here. What is interesting is to look at its equation of motion, so at the classical level, because these fields are boson also, so they can be highly excited. And this is the situation we're going to look at. A very simple way to write it is you can do exactly the same than in general relativity when you go from flat space to curved space. If you go from abelian to non-abelian, you can replace every derivative that you have by a group covariant derivative, and then you just get the correct equation of motion. So for instance, the equation of motion for the gauge field are just d mu g mu nu equals g nu, where d mu is a correct covariant derivative for the field strength tensor that is now also an object at transfer. And this covariant derivative, like in the U1 case, is just built to make this equation covariant, meaning that they transform in the same way on both sides. And the covariant derivative is also just built with commutator, d mu g mu nu is equal to d mu g mu nu. And then you have this commuting bit that again makes everything much more complicated. And J mu is also the vector current, but now the non-abelian vector current. So to GPQB. And then you have the imaginary part of phi dagger TA phi TA. And TA are just poly matrices, which are the generator of SU2 normalized in our convention. And actually, so one of the differences is not going to be crucial for here, but under some, I mean, even contrary to electromagnetism, which is a free theory, you see that these equations are not free. Even if J mu is equal to 0, you have some non-trivial solution. So even in the absence of matter, the field's equation are not solved by plane waves. And this is really because you have this commutator. So it's like a nonlinear equation even at the classical level. Solutions. So this, in principle, if you were to do all the things that you learned this week, yeah, there should be a sorry, why did I miss a mu index on the here? Yeah, I forgot the derivative. That's true. Thank you. So even in the yeah, and so even if you wanted to do all that you learned this week without the FLRW, so just look at classical equation of motion of field without the metric, that's the equation that you would have to solve, and that's what we're going to discuss after. Adding the FLRW metric is not a huge complication, and it's just add some friction term like you had in the abelian case that you saw yesterday with Paco. And the trick is really, again, you just can replace the normal now Minkowski derivative by the covariant derivative from GR now. And this brings you to the non-flat equation of motion. And something I'm not going to derive today, but you can find in textbook, or actually you can prove yourself. It's kind of a nice exercise. When you have a vector field, like vector in the sense of a tensor in the sense of general relativity, so two-index field, there is a nice expression to find the covariant derivative, which doesn't need the Christoffel symbol and all of that. You can compute it as a dg mu nu. Let me maybe, yeah, dg mu nu by dx mu, which is actually somehow simpler than putting all the Christoffel symbol. But this I'm going to let as an exercise.
Adrian, don't you need the square root of g also inside the parentheses for the derivative? Or
yeah, sorry, I'm still a bit sleepy. And so if you do that, you get the following equation of motion for g. Now that I'm going to write, so separating the spatial part and the temporal part. 1 minus alpha gj I, and then 1 minus alpha a prime a times g0 I. So this alpha, again, it's this alpha time that we introduced that we use in CosmoLattice. If you want to switch from conformal to physical time, you just need to put alpha 1 or 0. And this is equal to the current A2 alpha GI. And again, the crucial part that plays an important role in the theory is that you also have Gauss law. That is the other set of equation. And this reads the same as in flat space. Bi G0 I is equal to A square G 0. And this is Gauss law. And when you're interested in looking at the non-abelian SU2 gauge field, these are really the set of equations that you need to solve together with the scalar part. The scalar part doesn't have any extra difficulty, so I'm really going to focus only on these two sets of equations, and then all that I say will apply also to the scalar part in a trivial way. But the conceptual difficulty really arises kind of discretizing this field and trying to put them on the lattice. So if so far so good, I can continue. Otherwise, I'm happy to take questions.
Is there any doubt?
Yeah, if I don't get any question, the lecture is probably going to be shorter, but that's okay. Okay, let me continue then. The second step is really to go to the discretization. And here, the first step, the first difference when you just have a scalar field is really like for U1, is you need to introduce this link variable to have the scalar field gauge, the scalar field covariant derivative covariant at the lattice level and to preserve gauge invariance. So now it's really that you don't want to use any variable that lives in the algebra of SU2, but you want to represent everything by something that lives on the group, because the transformation of the group is doesn't involve derivative. So when you go to the discrete equation of motion, you can preserve this transformation in a simple way. Minus I G B Q B delta X B mu. And this belongs to the group now. And you can check that now this transform in a simple way also, because you go from again the algebra to the group. And this is the nice transformation property that it transforms like omega at the point x times u mu times omega dagger at the point x plus mu, where this plus mu is really meaning I shift in the direction mu. And so this is just a simple generalization of what you saw yesterday with U1, and this is what enters the covariant derivative for the scalar field also. The big difference for the non-abelian is that now, since the field strength tensor itself transform, you don't have the freedom of discretizing f mu nu with a simple derivative and keep it gauge invariant like it was done for U1. You need to have g mu nu expressed through links also, which corresponds to this non-compact formulation in U1. But this is not a choice now, it's really a mandatory feature. Because if you try to express it as derivative of some b mu, you're never going to be able to write an expression that is gauge invariant at every lattice point for finite lattice spacing. And the reason behind that is that the derivation that you saw in U1 yesterday breaks down because of the commutator b mu and b nu. This is going to screw up your transformation if you try to to just do it by doing a normal forward or backward derivative of b mu and write g mu nu like that. And so the strategy is really to find some operator O that depends on U, so any links at any point, that has the correct transformation property, namely omega x O omega x. And if you find such an operator, then you can try to check at least it's a good candidate because it has the same transformation than G mu nu, and you can check whether when you take the continuum limit, it reproduces the correct operator or not, if it's really encodes the information of G mu nu or not. And so no suspense, I'm just going to show you what's the correct operator and then try to explain when it makes sense. For that, let me just introduce some notation. I'm going to write U mu with a subindex plus nu, the gauge link that is displaced by a unit vector in the direction nu. And this is going to be convenient because now I'm going to start to talk about loop operator and all of that, and I'm going to like multiply a lot of this matrix, and it's going to make it much easier. And so also this trusted operator actually is not unique. You have some freedom, and this corresponds really to the fact that also in the Yuan case you have some freedom because we did like a simple forward derivative, but you can do more complete, more precise or more a derivative with higher order derivative if you want that are more precise in the lattice spacing. Here you can do the same. You could have different operator that converge with a different precision in the continuum. But the simplest one is what is called the plaquette operator. And this is going to be the smallest Wilson loop that you can write on the lattice and has the correct property and goes to the correct operator in the continuum. So I'm going to write this operator by U mu nu. And it's a closed loop made out of this other U mu operator. So you start at point mu, then in the direction mu, then you go U mu plus mu, and then you have U mu plus nu, dagger, and U nu. The way to think about this operator is not so complicated. Is that if you have a lattice with different points. Now, the way to think about this link operator, and that's where the name comes from, is that they live on the link of the lattice. So at every point, for instance, in 2 dimension, you have 2 links. You have ux and uy. And now, when you move by 1 point, this guy, if you say, for instance, I want to look at uxy. This one is this first ux, then this one is the second uy at plus x, and the 2 dagger that you have at the end, I forgot the last dagger when I wrote it, they just tells you that you're going in the other direction. So now I am at u plus nu here, and I go in the other direction. So it's really this link here. It's the u x plus the ux plus y, and then I have the uy dagger, and I have a closed loop. And if you do the expansion of this closed loop, what you will find is that it has the correct continuum limit, in the sense that, let me write this here, uij. If now you take the limit of small a, this goes like the identity minus I, G, b qb delta x square j I j. And order by order, it's always going to be an expansion in powers of jij. gb square qb square over 2 delta x to the 4 jij jij plus O of delta x to the 6. And so now, and actually it's a good exercise to show that it works. Show this. But the trick basically, the fact that it works is also the kind of a statement of gauge invariant, is that this operator u mu nu is a covariant, so transform with the correct transformation in the discrete, but also in the continuum. So when you do an expansion in the continuum, you will need to have operators that have the correct transformation. No, and these are the GIJ. And what is good is that now you can use this all these building blocks to discretize the equation of motion. For instance, you can just use that in the covariant derivative as you did for u1. So d mu I phi is just going to be d mu phi is going to be u mu phi plus mu minus phi divided by delta x. And you can also use it to discretize the covariant derivative of the gauge field, which is important. And here it's going to be done in a similar spirit but at the level of the u. And in the actually, I'm going to give you the backward one because this is the one that somehow, I mean, you can use the forward or the backward, but the backward one is the one we use in the equation of motion in CosmoLattice. So let me write this expression. And maybe let's explain it a little bit. U I minus I dagger divided by delta x. And this is, maybe it kind of looks like an arbitrary expression, but it's really built in the very same way that you would do for the scalar field, for instance. This discretized covariant derivative, the way to think about them is really that a normal derivative, let's say if I wanted to write di gij, I would simply let me maybe say it for the scalar field, and then I can say for gij. If you wanted to write di phi, for instance, what you would write is just phi plus I minus phi divided by the delta x. But we know that it's a normal derivative, so it cannot have the correct property under gauge transformation. So the way to correct that, it's always to insert this u here. And the thing that it does is that it really corrects it. The problem with this derivative is that since gauge transformation are local, this field is not going to transform in the same way than this field. And inserting this u is just a way of correcting this transformation by moving on the group manifold in the correct way, correcting the transformation, and then bringing the field back. And the idea of this u's here are exactly the same. Now, this object uji also transform in a non-trivial way. So if you move it by one lattice spacing, you need to correct its transformation so that its transformation is the same that this uij. And then thanks to this expansion here, going from Gij or Uij, when you take the difference, is the same because it removes this identity operator, and at leading order, you're just going to take a difference of the Gij. Good. So that thing is the time evolution, and in practice, it's basically very similar to what I was explaining. I mean, most of it is exactly the same as what I was explaining on Monday. And also basically the same that what Paco explained for abelian field. So normally what we do is that we set B0 is equal to 0. So we go to temporal gauge. And equivalently, this sets the temporal link to the identity. And once you're in temporal gauge, it makes things much easier because the conjugate variable to Gij, so the electric field in U1, if you want, so the non-abelian electric field, this is equal to D0 G0I. And this also means that since J0I is equal to D0 GI now, and you don't have any commutator, in this gauge, the electric field is again D0 BI.
BI, yeah.
The electric field is again abelian, and you can treat it as an abelian field, and it's only the magnetic part, so Gij, that is non-abelian. And this is really good because that means that you can use the same canonical momentum as you would do for abelian field, and all the non-abelian problems and using this bracket and all of that only happens for the magnetic field. You can use as a momentum conjugate really directly J0I as is, so without using the bracket. And then the Hamiltonian equation of motion that you want to solve is really by I prime, so here it's really the time derivative, is equal to A1 plus alpha plus A alpha minus 1 plus this expression for the covariant derivative I of u. And this is equal to the kernel. And this cov I of u is just a notation that I'm using just to distinguish, to say that this is really in the discretized version of the covariant derivative. Good. So this is the equation that that you need to solve, and actually you can apply all the same algorithm that we already saw.
Sorry, Adrian, I'm not following your notation right now. Pi I is who? The conjugate momentum of whom? Sorry.
Of G0I that I introduced here.
So what do you mean this is equal to the scale factor to some power plus something?
Oh, sorry, I forgot the current. Just the current plus the covariant derivative. This is the kernel for the non-abelian field. Yes, and then once you have this equation, you can use all the same algorithm. So velocity Verlet, Runge-Kutta, whatever you like, or all of them really. So yeah, let me not write, because maybe I'm not gonna write all of them, and then you're gonna come back and you will be, why can't you use this one? But you can use all the one that we talked about now for this equation. So, there is one subtlety that arises in the non-abelian case. subtotal t is how you apply the drift. Because now you need to have a way to relate ui to pi I, but pi I is this abelian field, so you need to find a way to do this exponentiation to go from the from pi I to ui. And this you can do in two different ways. That are equivalent in the continuum limit. So for small dx. I think I'm going a little bit faster than what I thought, so I think it's a good moment to take a break now, maybe to absorb, and then I am happy to answer some questions, and then I can explain that, and then I can show you a bit how it works in the code.
That's fine. Yeah, let's make a 5 minutes break then, and please, people feel free to ask questions on these obviously more difficult aspects now. If you have questions, maybe raise up your electronic hand, please, so I can let you in.
Just gonna get some water and see if there is any question when I come back. Yeah, I had a doubt when I wrote it before, but I forgot this factor of GB, QB, delta X square in the discretized covariant derivative also, because of course, otherwise you don't get the correct normalization. But this is just a factor. Also, again, whenever you have a doubt, and this I think is true for a lecture, but maybe even more for this one where I'm writing live, if you have a doubt in the expression, you should go check in the CosmoLattice manual or in the expression or in anywhere else in the literature. But you should take that for the concept, the equation. You should go check them in the documents. I think it's important to say. Yeah. Good. So maybe we can restart. So let me explain you how you do this this drift. Let make a few comments, and then we can go have a look together at in the code and have a early coffee break. So the first way you can take make this drift works. I'm gonna call solution number 1. Is that you just write explicitly already in the continuum what's the time derivative of the link. So by that I say, you really say, okay, so I know that in the continuum this link variable is e to the minus I GB QB delta X BI prime. And then this is simply equal to minus I GB QB delta X BI prime multiplied by UI plus, of course, since it's not abelian, now you're making some mistake because neglecting the commutator.
Adrian, I'm not sure where you are writing, but I see a static picture of your screen.
Oh, sorry. It's not, you're not seeing the...
Now I do,
okay.
but not before.
Okay. Well, so yeah, so what I wrote is this part here. That you have this solution number 1. So again, you just take the derivative in the continuum, and you pay a price of some commutator that you're neglecting. But you can say that at the first order in the x, now this derivative is just equal to the derivative of the gauge field times the link. And the way then you take your drift is that you rewrite that in terms of the conjugate momentum, QB over A1 minus alpha delta X by IB UI. Still this term that we are neglecting, and I'm keeping it just to make clear that now, and this is a bit different than in other places, but here you add an extra mistake at the level of the drift. And then a simple way of applying this drift is just to invert this relation. Inverse this relation for ui at time plus 0. And this gives you a first way of doing the drift. This is the one I believe we implement in the code. We can go check this after together. And in principle, you have a second solution that works best for SU2. All the thing I'm explaining now also works for SUN in general. This solution too, I think you can make it work for SUN also, but it's probably not super efficient. And the reason is that another way to do it is just to compute explicitly U0i. So this gauge link that normally you don't have because U0i is the one that you would use for G0i. And G0i, we said, okay, in temporal gauge, it's abelian, so I can just treat it as is per se. But you can also say that U0I is the exponential of minus I GB QB delta T by I A1 minus alpha. And then if you're able to compute that, so this metric exponentiation, then you can say that U0I, well, actually it's that, but it should also be UI plus 0, UI dagger. And this gives you another expression, UI plus 0, U0I, UI. And so this is kind of a nice trick to do also, but it's easy for SU2. Sorry, easy for SU2 because you have an explicit expression for this exponential map. But but not so much for other group. Because the exponential map becomes harder and harder to compute as you have larger n. And so in practice, if every time you need to compute this U0I using some algorithm to compute the exponential map, it's easier to do the solution one. But since we are most interested in SU2, you can really choose between these two methods. So just to make it very explicit, let me write this, how it looks in the case of leapfrog. So for solution 1, solution 1. And this is just to clarify by what I meant, invert this relation for U0I. So the leapfrog scheme is that this momentum pi b, I at time 0 over 2, so dt over 2, is equal to pi I at time minus 0 over 2 p plus the kernel. So this is just the kicks, nothing special. And now the drift, you write that ui at times plus 0 is equal to ui. And then you just need to construct the field ui at time 0. So the way that you do it is like that. You write I G B Q B delta X delta T A1 minus alpha 1 alpha, and then you have, you have your pi p I a over 2, so really that comes from here. And now you just have a little doubt of what I'm writing. Okay, and then you just multiply it by the gauge field as we saw here. Sorry, I think I just used a poor notation in my notes that I'm trying to understand right now. Give me 1 second. Yeah, sorry. I need to correct my notes because I wrote something something wrong there. So the subtlety when you do this drift is that you need to evaluate this pi I at time 0 at time a half that you just computed here, but this from this expression here is multiplied by a link that is also evolved at time dt over 2. And the problem is that you don't know what this link is a priori because the link in leapfrog lives at integer time. So the way to go around that is to do an interpolation and to write that this link that lives at half dt is equal simply to the link that lives at minus a half minus dt, sorry, that lives at dt. So ui plus the link that lives at ui plus a half divided by 2. And so once you do that, you see that you have an equation, plus full-time integer. So now that you have that, you see that you have an equation where you have ui plus of 0 on both sides, and you just need to isolate this ui of 0. And so when you do this inversion, you find an equation for ui at times plus 0, and this is just equal to 1 minus I GB QB delta X delta T divided by A1 minus alpha alpha of pi I 0 over 2 square times UI. And so really just to clarify what I just did again, you have this expression on the left for the time evolution of the link, and you see that this is equal to pi times u. The only subtlety with that is that again, when you have this expression that are discretized on the lattice, they leave, if you want, at some point in space. But once you do some time evolution, you also need to evaluate them at the same moment in time. And so, for instance, when you do this leapfrog scheme, this introduced this extra difficulty that now the scheme, the leapfrog scheme on the right evolves. You need to evaluate the momentum at time a half because that's where the momentum lives. But this momentum, since it comes from this time derivative of the link itself, also involves the link. And the link doesn't live normally at this half integer time step. So to have a good expression that gives a scheme to the right order, you need to interpolate this link at half a time step by doing this trick of just summing the two links and dividing it by 2. And now you have some sort of here it's, if you want, a simple example of an implicit scheme in some sense, that ui plus 0 also depends on ui plus 0. So the way to go about it is to invert it, and an approximate, and if you work this out, up to O of dt square, an approximate way of doing this inversion is to write it like that. And this is simply the fact that you can write that as we can do, since we have a bit of time, we can do it explicitly if you want. You can write this this equation star here as ui plus 0 is equal minus ui if you want. Oh, let's keep the ui on the other way. So is equal to ui minus I g b q b delta x delta t divided by a1 minus alpha a half. And then you have pi I 0 over 2 b. Then you have a ui, this is not a problem, times ui divided by 2. but then you also have this expression that I'm going to pass on the other way. So on this side, you have a plus I, G, B, Q, B, delta X, delta T, divided by A1 minus alpha 1/2 times, let me just move this because this was too close. Times pi I 0 over 2 times ui plus 0 plus that. So you see that left and right, you have you can rewrite this equation as being 1 plus I GB QB delta X delta T divided by A minus alpha 1/2 times pi I 0 1/2 times ui plus 0. And this is equal to 1 minus GB QB delta X delta T A1 minus alpha 1/2 times ui. And then the expression that I wrote here is solving this equation by doing a little extra approximation. Is just saying that you see in like the exact expression for ui is saying that ui plus 0 is equal to 1 minus GB QB delta X delta T divided by A minus alpha 1/2 ui divided by 1 minus GB, and of course I forgot the pi here, and that's why it's important. For 2 GB QB delta X delta T A1 minus alpha 1/2 times pi I 0 2 pi I 0 2.
It's a plus.
Yeah. And so you see, in principle, you can solve that exactly here. But since you already paid some O of delta x squared before, it's better just to do an extra Taylor expansion and write that as 1 minus GB QB delta x delta t divided by A1 minus alpha 1/2 by I 0 over 2 square times ui. And again, this is simply because we are working with this matrix pi I. And since matrix inversion are relatively complicated, since you're already working only at O of dx squared, it's better just to do this expansion. And so you don't need to invert the matrix, but you just need to compute the square.
The imaginary roots
this is what
disappeared, Adrian. I don't know if this is on purpose.
What happened?
Imaginary I roots that you had originally.
No, they just disappeared. Okay, so this was just to try to clarify that. I have some poor notation in the notes that Danny uploaded. I'm gonna send some corrected version also. Okay, and that's good. There is a last subtlety that I didn't want to comment on, but since we have time, maybe I can still comment. Actually, there is just an extra little difficulty is that you see that this, strictly speaking, is not a group element, but it's really something that lives in the algebra. So the way that you solve that is that you reproject it on the group when you do the expression, and this allows you to keep something more stable, and you're sure that you don't wander off the group manifold. But that's really a technical detail. Conceptually, it's just you need to solve this drift. You need to link this somehow you need to leak this momentum to this link so that you can do the evolution in time of the link. So you compute the derivative in the continuum, and then you just invert this relation to find the expression for the link in the next time slice. Cool. So we are almost ready to go to the code. Last thing I want to comment on is Gauss law, because I think it's really important. And this is something that is kind of nice to know at the conceptual level. In the Hamiltonian formalism, gauge invariance is completely equivalent to Gauss law. And in particular, the fact that we are preserving gauge invariance at the discrete level, it manifests itself in the fact that you have an exact conservation of Gauss law. Exact conservation of Gauss law. And the reason I'm saying that is that you can see that easily from starting from a Lagrangian, is that Gauss law is really associated to the equation of motion of A0 that then you gauge fix. And it's really if you want, the Noether current associated to gauge transformation, and it's also, you can also think of it as the generator of gauge transformation. It's the conservation current from shifts in A0. This is also true in the abelian case, by the way. It's really something that is general, and this is a gauge transformation. So it's going to generate all the remaining gauge transformation that you have once you fix your temporal gauge. And the fact that it's conserved because you implemented the symmetry correctly is very analogous to this angular momentum example that I was presenting on Monday. This is kind of why I insisted so much on that. I mean, to be clear, the conservation law is different in the sense that this is really a local gauge invariance. What I mean is that the fact that when you respect symmetries, this corresponds to to exact conservation of the associated Noether current. This is what I want to say. Good. I think that's all we need to know for the gauge field. One thing I'm not going to talk about is the initial condition, because they are basically the same than for U1. Similar to U1. And now I think we're ready just to see how this goes in the code. So I'm going to shift from here to the code, if this works with you. The code that is here, yes. Oh, sorry. Maybe let's start with the model. Can you see the code?
We don't see the file yet. Now we do. Now it came up.
Is the font screen appropriate, or should I zoom a little bit?
I think they are big enough. Thank you.
Okay. So now, if you want to use this gauge field with CosmoLattice, the third thing, if you don't want to even sort of remember what I said, you can already look at this example file in the model file. Again, the equation of motion for matter are not going to change. So the only thing that you have to do in some sense, if you're happy with just having the gauge thing evolving by themselves, is to change the potential again. And change the number of fields that you have again in this default model parameters. So this parameters here tells you how many doublet and how many gauge field that you have. For some technical reason related to the gauge coupling, you can, in the implementation that we have now, you can use only one gauge field. In principle, you can use as many doublets as you want, and you can give them different charges with respect to the gauge field. The rest is all the same that you have looked before. You also need to specify this these two new coupling manager. So just again, number of SU2 doublet, and you need to tell them whether they couple to your U1 field or not, because maybe you won't have a model where the doublet couples only to the SU2 gauge field and not to the U1 gauge field. The fact that it couples to U1 just comes from the fact that they are two charged scalar fields. So, like, really, if you see them, U1 is going to see them as two charged scalar fields that have the same charge, and you need to say whether they couple to it or not. Then you also need to say whether they couple to SU2 or not, which probably you want them to couple to SU2, but maybe you don't. Then all the rest is similar, except that now, as Paco showed for the initial condition, here we are reading some norm for the initial condition. So the way we do it is that we just put a homogeneous field in the zero condition in this example, for instance. Here, we put we get the norm of the SU2 doublet, and then we put the same strengths of the norm in all different conditions. So this is the initial condition for the fields. 0C again means that it's the first doublet, and it's really treated as complex scalar field. And this function make SU2 doublet just create a SU2 doublet that is constant and that has the same constant in all components. This is all the same as before. And then again, at the level of the model, not so much changes here. In this model, we just have a scalar and a doublet. And the potential that we're looking at is just lambda phi to the 4 for the doublet, and then some interaction between the SU2 doublet and the scalar field, and the same here. And then we write down the derivative with respect to the field. So first, you have the normal one that are with respect to the scalar field, and then you need to look at the derivative with respect to the complex scalar field and with respect to the doublet. And as in the case of U1, we always write the derivative in terms of the norm of the SU2 scalar field, because it will have to depend on the norm since it's gauge invariant, and it's often easier to write the derivative, and then this derivative with respect to the norm are converted with respect to components inside the code somewhere. And then same again, for initial condition, you often need to know the second derivative of the potential that gives you some effective mass, and you write them explicitly here also. What is maybe more interesting is to go look a little bit inside the code how these SU2 fields are implemented, and see that actually that's one of the, I think, really thing that is unique to CosmoLattice is that all this kind of complicated algebra that I described today are implemented in a sort of very user-friendly way. You don't need to write any matrix. You don't even realize that you're working with matrix, which which makes the coding much easier. So if we go in the Cosmo interface, for instance, we can go look at how this leapfrog scheme that I just explained is implemented for the non-abelian fields. And actually, the way it is done here is that I'm just writing this function as evolution of the momentum that live at half time step and the field that live at integer time step, as I described before. And all the different fields are implemented in this function. The sequence that I want to show you is really this kick SU2 doublet followed by the drift SU2 vector. And I mean, yeah, the kick SU2 doublet, kick SU2 vector, and drift SU2 doublet and drift SU2 vector. So again, the name tells you that SU2 doublet is really just a matter field, and the SU2 vector is the field strength tensor. The relevant functions are these kicks, and so kick SU2 doublet is very simple, implemented like all the other field. You just add to the momentum the kernel that is written in this SU2 kernel function. I think it's also nice to have a look at the kernel because it gives you some idea, again, of this nice syntax that we have in CosmoLattice. So the SU2 kernel is this file here, and is again simply you have this function that computes the covariant derivative for the SU2 doublet, and then you have the derivative of the SU2 doublet itself. And this is basically the function that maps the derivative of the potential with respect to the norm to the one with respect to components. Something then, okay, I am not going to go through all the kernels one by one because this is going to be a little bit boring. We can still look at the kernel for the SU2 vector, and then I can maybe show you inside the function of this kernel also. The kernel for the SU2 vector is in principle is the one that is most complicated, because if you remember what I wrote before, it involves this covariant derivative. And this covariant derivative also involves the computation of this bracket operator, and you need to sum over all direction and because it's really a divergence that you're computing. And this is what is done at the level of this function. This computes the sum of the plaquette that is relevant to the covariant derivative. And to do that, you have this plaquette function that really just takes the links that are stored in this FL field SU2 variable n. N is just in principle is just to call if in principle you had more than one gauge field, which we are not doing here, but you could do that for a different gauge field. The point here is that you take your gauge field, you give it to this plaquette operator, and it computes the plaquette in the direction I and j. And then you for the three different directions that you have, you compute the sum over j, which corresponds to taking the divergence. And then the actual covariant derivative is this sum of plaquette minus the sum of the plaquette that is with this multiplication of these two links, so that is corrected to have the correct transformation once you shift it by a side j. And then in the end, the full kernel for the gauge field, you can just write it in terms of this expression. So this expression, if you write them in paper or if you try to code them yourself, are very complicated because you have it's really like these SU2 matrices, and you need to do 4 multiplication of SU2 matrix here, 4 multiplication of SU2 matrix here, and you need to solve this equation for every entry of every matrix and for 3 dimension, because you have like 3 vector 1 pi dimension. So in total here, in one line of equation, we are returning kernels for nine different components, because every vector field has 3 non-trivial entry, and you have 3, because it's a matrix, so 3 fields per matrix, and you have 3 of these vector fields. So this is really like 9 equations returned in a single line. The thing I like to show also is how this bracket function are implemented, because again, it's a 4 multiplication of matrix, but in CosmoLattice you can literally write it as you would do on paper as a 4 multiplication of matrix, but without doing the matrix multiplication explicitly. And also this allows me to show a little bit the structure of this template that is, if you want, this black box usually, we call it. And this bracket operator is stored in this lattice folder, and then you have this algebra, and you have this gauge algebra, and you have a lot of different operation to compute magnetic field, brackets, some exponential. But the bracket itself is kind of pretty easy to see what it does. And it's really literally, again, implemented like an algebra at the level of the field. This bracket function gets some expression that will represent the first link, the link that you want to take the bracket from, and then some 2 directions, mu and nu. And then it literally implements the expression that I wrote on paper before. It computes u evaluated at point mu, and then you shift nu in the direction mu, and then with the daggers you compute the shift of mu in the direction nu, and then just the dagger of u in direction u. It's really just a simple bracket. And in principle, if now you want, I'm showing you that because maybe for some reason you want to consider a model that you don't have only plaquette, which are this like smallest Wilson loop, but maybe you will have a plaquette with 6 links, with 8 links, with 12 links, or whatever, a more complicated loop. Maybe you actually want to compute some Wilson loops in your simulation because you're interested in something that involves Wilson loops. And in this sense, if any of this operator will be very easy to implement, because you can just take this link and shift them around and take multiplication of them. Yeah, so that's, I think, basically it for the leapfrog. Maybe I can show also how the drift is implemented, since I spent some time to talk about it. So for, of course, the scalar field, there is no, for the doublet, there is absolutely no subtlety. It's just the same as usual. You just add dt times the momentum. The drift for the vector is what I wrote here, and is really this rescaled pi, just compute this 1 minus pi that I computed, that I explained before in this way here. And here it used the trick that you're in SU2. So it's basically, you can see that if you go inside the function, this is what this rescaled pi is really this 1 minus, and then I just square it, and I multiply by the field at position, the field, the n number field, and that does the trick. Yeah, I think this is probably enough. I'm happy to show other things if you have questions about the code, or take any other question, but that's basically what I wanted to say here.
Okay, thank you, Adrian. I guess this lecture is a bit harder than the usual ones or the previous ones. Feel free to ask something if you have doubts now in real time, or surely you can ask your doubts afterwards, tomorrow or any other day. Yeah, perhaps it's recommendable that using Adrian's notes as uploaded in Indico, well, he will send the corrected ones.
Yeah.
Typos. You also go to the manual and have a look in parallel, you know, to many of these expressions. So there is a question, Adrian.
Yeah, sure.
Submit yourself. You can go ahead.
Hello.
Yeah.
Can you hear
Hi.
me?
Yes.
Okay. Yeah, first off, thank you for the talk. And I would like to ask. So, like currently, there's no way to sort of modify initial fluctuation. Like, am I right? Other than like going into the templates and.
Yeah, exactly. It's the same that for U1. You need to. No, it's not in template. It's really on the this gray box. So it's really in this Cosmo in this Cosmo interface. It's this in this initializer.
Okay. Okay.
You see that you have this SU2 initializer, and you need to go in there. You really need to be careful about Gauss law, though. What is tricky is that. So there are kind of two ways to do initial condition for gauge field. One is basically the one we're following here, is that you find some fluctuation that makes sense and that actually directly satisfy Gauss law. And to do that, we exactly do the same. It's just a simple generalization of what Paco explained. You basically set some of the fluctuation, and then you solve Gauss law in momentum space explicitly to just impose Gauss law. In principle, there is an alternative way, which is you put arbitrary initial condition that don't that violate Gauss law, and then you do some minimization to impose Gauss law very explicitly, and this is called gauge cooling, and this is not implemented in the current version of CosmoLattice. So if you want to impose your own initial condition, you need to be really sure that your condition actually satisfies Gauss law, and this is kind of the tricky bit of it. But up to that, you can just go and modify the function and put your own function. The thing I was trying to say in answering this question too long is that that's why some of this, that's why this procedure is kind of complicated. It's just to make really sure that Gauss law is imposed initially.
Right. I see. I'm thinking like, could I actually like just attack this problem in another approach? Maybe I could just save like the current simulation and then like roll the directory like back to the previous simulation, and then I change the initial condition for well, sort of like because like the potential I want was sort of like through time, then it would sort of decrease the fluctuation, and so
Yeah.
you get like a phi square potential. Yeah. So maybe in that sense, I could go back and then run the directory again, and then like run the previous simulation again, and that could solve the problem. Like but yeah, at the same time changing the initial phi value back to the position I want. But then I'm not sure whether because
Yeah, I mean, I don't know if it makes sense physically for your model, but in principle, what you could do, I don't know if it makes sense, but you could, like physically, I mean, but in terms of like evolving the equation, it's going to be okay. What you could do is to do some simulation with some parameters, some value for phi, get some value, some configuration of the gauge field and of the doublet that satisfy Gauss law, and then use that as initial condition for another simulation with, say, other scalar field or even other matter content. I mean, it's self-consistent. I don't know if it makes sense, but it's self-consistent.
One feature I think we haven't highlighted much, or maybe not at all, I don't remember right now, is the fact that CosmoLattice is prepared to do what Adrian just said. So you can output the whole distribution of your fields and load them as initial condition for the next run, you know, and as long as the size matches, no, and the same number of fields, etc., you can literally do these kind of things. This is useful for even a scenario where you want to take a break in your run because it's taking too long, or in your
Yeah.
class it's a limiting time, or doing some exercise of the kind that Show is asking. Yeah.
Yeah. The only thing, if you do that, Show, you may run into some trouble that are not real trouble. That there may be some checks that you have the same field content or not when you restart, because just normally you want the same field content, but these are just like kind of checks. And if you run into problem, you can always ask us, and I can show you which line you should remove.
That would be great. And I just want to confirm again, like so like in the manual it says there are like certain parameters we couldn't override when we start like a safe simulation, like are there like
yeah, so that's also what I had in mind. This is just like a sanity check, because normally you don't want to override them when you just, because this feature is implemented to restart the simulation. So in principle, you don't want to change this parameter, and it kind of doesn't make sense to change them. So these are the parameter you cannot override, but it's really just the safety feature. If you actually know what you're doing and you actually want to override this parameter, you can just change the type of the parameter inside the code. And if you need, I can show you how to do it.
No, that would be great. Thank you.
Okay, I think there is another question by Tucker in the chat. Tucker, do you want to speak out loud?
Yeah.
Yeah.
So if you
go ahead, Adrian.
Yeah, no, it's because it's computationally more expensive, and for like typical, I don't know, heating or like that is not necessarily what you want to look at. But I mean, the main reason is really just because it's more expensive.
The question has
Yeah, the question is, Tucker is asking why we don't do SU3, and whether it's just because it's too expensive. And the short answer is yes. It's not even too expensive, it's just more expensive. And so you want to focus your resource where you really want to ask the question. But ideally, if you have enough resources, it's nice to do SU3 also. And it's not implemented on CosmoLattice, but it's mostly out of, because we have finite time. But this is really not something, I mean, the way, if you go look at how SU2 is implemented, the only thing that you need to do to implement SU3 is to implement the SU3 algebra, which is kind of painful, but except for that. You can do SUN in principle, but that becomes harder and harder.
Thanks.
Good. More questions? Okay, doesn't look like. Well, I give you a couple of minutes to think about it, but meanwhile, I led you with the link to the new YouTube channel that we started yesterday, where you can find the lectures, the videos so far from Monday and Tuesday. I will upload the lectures from today later on, and so on every day. And well, you were asking for them. I guess we will send them. We will send this link via email to the participants, and also we will put it in the website.
Okay, in the meantime, I'm gonna correct my lecture that I sent you.
Okay.
Hello, I have a question.
Go ahead.
Yeah, sure.
When I want to restart the simulation, does the CosmoLattice read the parameter from the H5 files?
Yes.
I think so, yes.
Yes, it does.
Yeah, thank you, Jorge. You used it like more recently, yeah. I let you answer because I kind of forgot.
Yeah, so CosmoLattice saves the parameters you use for the simulation in one of the data sets of the H5 file, and then it reads them again. So you can just rerun the simulation using without having to input any additional input parameter. But you also have the option of changing the parameters when you rerun the simulation.
So it means that when I want to restart the simulation, I can write a H5 files which include all the parameters in my model and the data of my lattice data point, right?
So you are thinking of starting the simulation from a configuration generated in an H5 file?
Yeah.
So you could do that, but you need to be very careful in the way in which the parameters in the H5 file are written, because the structure, so when you are trying to read the parameters like the time step and the number of points per dimension and those things from the H5 file, the function which is implemented in CosmoLattice is quite strict. So it's not supposed to, it's not supposing that you are writing the H5 file. It's supposing that you are using an H5 file that has been produced by CosmoLattice.
So yeah, probably if you want to do that, the simple thing to do is to generate an HDF file from CosmoLattice, like a very small lattice, so that you can actually open the HDF file and look at all the data set and what names the parameters are, and then just use these names when you write your own HDF file from Mathematica, Python, or whatever.
Yes, it's a great idea. Thank you.
Yeah, and in particular, be very careful when you do these things with the H5 files, because CosmoLattice assumes you are using a particular encoding for the H5 files datasets. And if you change something, you need to keep the same encoding for the type of numbers and the type of, especially for the type of, in the parameter part, the parameters are stored as characters, and you need to use the same encoding for the characters.
Okay.
Which you can check in the H5 file, but I'm doing the thing that Adrian suggested is the best option if you try to do something like that. But you need to be careful of the character encoding, because that's otherwise not gonna work. It won't read the parameter.
But on the positive side, it's definitely doable, because I know at least two persons, which are Jorge and Toby, that did it on their own. So
yeah.
Okay, any other question? If not, I think we can leave it here. Well, I mean, we are happy to be here for more questions, yes? Okay, I thought somebody was saying something. Yeah, I guess thanks a lot, and see you tomorrow, everybody.
Thank you.
Bye-bye.